So maybe just some wording. I didn't introduce it earlier because we don't study this in detail, but just we say that f, which is a priori defined in some area, some domain minus a few points, is meromorphic if these singularities are either removable, and then f is holomorphic there, or full. So no essential singularities. Okay. So not that this word brings a lot to us, but here is the so applications of Cauchy residue theorem. Suppose we have some domain. So here, so G is simply connected domain, just like in the theorem, and F is so H is a function so it's meromorphic at G, which means that so we have some points A1, AM, F is holomorphic in the complement, and AIs not essential. So in this situation, one can talk about the divisor of F. So it's a formal linear combination of points. So finite linear combination of points. So let me write it d of f it's sum over all zeros of f in G, say bi times, so bi is a point, times order of 0, minus sum poles of f in G, A, say J, again times order of pole. So it's your choice either to consider this as a combination of all points from G or just what I wrote, because if a point is neither 0 nor a pole, of course order will be 0, so this point will just disappear. So let me give an example. So suppose my function f is something like 1 over z minus 1 squared minus 3 z minus 2 plus z minus 3 cubed. Then what will be the divisor of f? It will be the following expression. Of course, I have the problem of denoting the points differently than numbers, but I have a pole of order 2 here, a pole of order 1 here, and 0 of order 3 here. Right? So I write 3, which is multiplicity, times, so to say, 3. So this is the point 3. Minus 2 times 1 minus 1 times 2. Okay. So this is a formal expression of a few points. So in this box, I mean, it's not a standard notation for a point, but I just need to distinguish the coefficient, the multiplicity, from the point itself. So that's why I'm writing something like this. Okay, so now why I'm writing this, it's for the following reason. So now coming to the theorem. So just changing the notation, so make it closer to the book. The function will be denoted by, say, h. Right? Okay, so I just maybe. So now we come to the theorem. And maybe I'll again draw a picture. So we have this area G. And then we have these points AJ and BI. So the 0 points and the pole points. And now we take the path, simple closed path gamma, which connects, which contains inside all these points, both zeros and poles. Okay. So then integral over gamma of h prime of z over h of z dz is sum of orders of 0 minus sum of orders of pole. So in notations from the book, it's z for zeros minus p for poles. So if we were talking about that example, the corresponding number would be equal to 0, because I would be subtracting 3 minus 2 minus 1. Okay. So now let me prove this. So in view of this Cauchy residue theorem, it's very simple. Only again I lost the coefficient. So proof. Let's apply Cauchy residue theorem to the function maybe capital F, which is h prime over h. So, so it's a nice function, and it's holomorphic outside of this divisor. So, mark f is holomorphic in G minus zeros and pose of f. So, so then the is sum of residues of f at pole points plus sum of residues of f at 0 points. So these are pole points. So we can study them one by one, and that's what I'll do now. So I just want to introduce a notation. It's not so you'll see the notation will be suggestive, but I don't mean by it that I'm choosing any kind of logarithm. So notation is that h prime of z dz over h of z is called d log of h of z. So it's notation. It's not any kind of. So I'm not defining symbol log here. I'm defining the symbol d log. So obviously d log in this notation exists. That's what it is. But properties are exactly like you would expect. So the notation is suggestive. So properties d log of h to the n of z. So what would you expect this to be if log were defined? Of course, log of any power is n times log. But even though log is not defined and we're talking about just this thing, you can calculate that this is n d log of h of z. In the same way, d log of 1 over h is minus d log of h of z. And d log of a product, h1, h2, is d log h1 plus d log h2. So again, I am not talking about logarithm here. I am just using this as a symbol for this expression, and if you want, you can independently check that for this expression these hold. Okay. So now there are two cases. So we are interested. So we have this function f of z, which is h prime of z over h of z. So we are interested in integral over maybe some little circle around AJ with some radius R, f of z dz, which is integral over some dk aj r d log h of z. Okay. Now suppose that, yeah, so aj and same for bj. Bi. So now there are two cases. So case number one, case of a 0 point. Right, so then we know that h of z at this point is z minus bi to some power ni with the n, okay, times g of z, where g of z is not 0 at bi, and g of z is holomorphic in some neighborhood. I mean, I'll be doing it locally in this little disk, so it doesn't matter. So now let's use my properties I outlined there. So integral dk bi r d log of z minus bi to ni times g of z. So g of z inside. Well, we have the properties to use. So this is ni integral over dk of bi r d log of z minus bi plus integral over the same circle d log g of z. So now, since I was using this just as a notation, let's go back to what we started. So then this is ni times integral of the same dk blah 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 of well, if you write what d log of this is, it's 1 over z minus bi dz plus integral over dk of something g prime of z over g of z dz. Now this is a holomorphic function. So since it's a holomorphic function, this is a contractible path, this part is 0. So we have only this, and this we get this as ni times, and we know what this is. So we are integrating around the circle, so it's 2pi. Okay. So this was the case of, so as you see, I used just the formulas over there, but again, I was not talking about logarithm, it was just a short calculation. Now, let's do the pole case. So now we have AJ is a pole of order, let's say MJ. So again, this means that in some neighborhood, H of Z becomes Z minus AJ 2 minus MJ times G of Z, where this guy is holomorphic, and G of AJ is not zero. Well, we repeat the calculation. We are doing integral over this small circle around now AJ, BJ, or AJ, some small radius r, d log of H of Z. So then d log of Z minus AJ MJ times G of Z. And that's where we use these rules, and it becomes minus MJ, minus MJ integral ZK dAJ r d log Z minus AJ plus something which will be zero. So this whole thing is holomorphic. So then we'll get just this. So summing up over the points, sum over the points. So integral 1 over 2 pi I, integral over gamma h prime of z, h of z, z becomes sum over zeros of multiplicity minus sum over poles multiplicity. So this is the formula I wanted. So I think at this point I'll make a mathematical remark. Expressions like d log h of z, or more generally say f of z dz appear often, are important, and are called now, do you know the name for them? When there's dz in the end. They're called differential forms. So in a way, when we integrate over a path something which looks like a function times dz, we're integrating a differential form. So you don't integrate functions over paths, you integrate differential forms. Good. So let's apply, or maybe let's get a corollary from this. So this is called principle of argument. So suppose we have a gamma, a path. We have a function h, a function. G, so f h g to c. Now, so we have this path gamma. So let's see. We have the original gamma. Gamma is a map from A, B to G. Gamma of A equals gamma of B. So the original interval from A to B, it maps by gamma to G, and this maps by H to complex numbers. So in particular, I can consider composition and call it capital gamma. So let's see. Let's see how we can modify left-hand side of this theorem. So we were integrating over gamma h prime of z dz over h of z. So this was integral from a to b of a h prime of gamma of t, gamma prime of t dt, divided by h of gamma of t. But using chain rule, we get that this is the same as the integral from a to b gamma prime of t dt over gamma of t. So then this is the same as simply integral over capital gamma dz over z. So So we know what this is. This is called variation of argument or winding number. So remark. The expression so this is variation of argument along the path gamma. So it's the same as winding number along the path gamma. Now, so the outcome of this theorem is so we have this G, this path which goes around all the zeros and poles, and then we apply H, and now this will become a new domain, maybe H of G in complex numbers, and we are taking H. This is gamma. So H of gamma, which was gamma star. And since H is complicated, it can go in different ways, but still returns. And now there's a way to calculate winding number of this path. So winding number becomes right hand side. So outcome right hand side, so these residue expressions of the previous theorem. Calculates the winding number of the path of the curve, closed curve. Gamma, which is H over. So in other words, you can take a loop around some zeros and poles, and then apply a function, and you can express the winding number of the image of this loop as sum of residues or of multiplicities of zeros and poles. Good. So we talk about this. Now another application is I'll probably announce it and start proving it. So, it's called Rochet theorem. It says the following. So suppose we have G, again a simply connected domain. And suppose we have two holomorphic functions, f and g. Or g. And we have the estimate. So now gamma is a simple closed path in G such that on gamma star we have that absolute value of f of z minus g of z is strictly less than the sum. Then and again I need a picture. Number of zeros of f inside gamma is equal to the number of zeros of G inside gamma with multiplicities. So you should think about it in the following way. So you have some simply connected domain G and a path gamma here. The point is that one of these functions f could be simple and the other could be complicated. So by finding zeros of f, we also find zeros of G. So you should think about following example when f maybe is a monomial z to the n, and G is some other polynomial of degree n. Okay? Then I'm kind of approximating one by the other. I mean, probably we won't have time for this today, but one of the applications of this is another proof of the main theorem of algebra. Good. So now let me prove the theorem. So notice that if a function takes 0, then this inequality becomes equality. So first observation is on the image of gamma, both functions are non-zero. So let's introduce a function f, which is, let's say, g divided by f. Then d log f is d log g minus d log f. So we have gamma star, the image of gamma. It's inside G tilde. So G tilde is this area where f of z is not zero. And this is inside G. And we have this function f. So notice that this inequality, inequality in the formulation reads like this. So it's so we have this even smaller set omega, which is exactly this holds. So then our path is inside by assumption. So we can treat f as a function on omega to g to c, and the inequality means this one. Means exactly that we land in the following. So it's the point 1 minus the negative rate. We had a name for it. This domain was called C pi. So f of omega is inside C pi. Well, now let's apply this principle of argument. So the integral of a gamma of d log f becomes the integral over, I would say, capital gamma, which is the image. So gamma is of, say, dw over w. But this path gamma star, whatever it is inside the area where a branch of logarithm is defined. So we are inside the area where 1 over w has a primitive. So then this integral is 0. Because this is a closed path. Okay, now let's open up what we obtained. So, integral over gamma f prime over f dz, small gamma, is integral over small gamma f prime, or sorry, g prime over g dz minus integral over gamma f prime over f dz, and is 0. So it follows that integral over gamma g prime over g equals integral over gamma f prime over f. But this is z of g inside the closed curve, and this is z of f. So we prove that, well, we proved that f and g have the same number of zeros inside gamma. So notice that since both f and g are holomorphic, there's no pole part in either of the sum. It's only zero part. Okay? So first thing we do on Thursday is apply this to reprove main theorem of algebra. So it's quite a strong tool.